Morning. All right, so we'll start. I would like to see how many people are here. Well, we'll wait a little bit more. There was some delay because it's another link and there was some password issues. So I entered a bit later. Anybody of you has a moment, has some questions before we start? Okay, it looks like the difference in the link is an issue. So I'll look in my email if there's anybody who wrote me that they have a problem. All right, okay, so. We will start from introducing the singular value decomposition, which I understood is not something which well, some of you know at least. Before we do so, okay, so I will not wait more for people. All right, so we are studying the statistics on, well, in fact, the behavior of the deformation tensor, this matrix of Jacobi, which is, I remind to you, is we consider Lagrangian. This is not good. Let's see if this works better. So we have trajectories of fluid particles, which are defined as trajectories which local velocities given by the local flow of the fluid, which we label by the initial positions. So Q at t equals 0 at x is x. So x is a continuous index. So we consider the matrix of transformations of the flow, which is of infinitesimal transformation of the flow, which is Wik dqitx dxk. So this matrix, as we discussed, tells us how the fluid volumes around some given point x are transformed in time, given that these volumes are infinitesimal. We want to describe this to know the behavior of this matrix because it would allow us to speak kind of to compare behavior of different pairs distinguished by their initial orientations, which start from the same point. So if we have this is the initial point, usually we consider that there is another nearby point x plus r, where r is well below the viscous scale, which, as we discussed, is a strongly fluctuating quantity if we consider large Reynolds number. And we wanted to study the evolution of this vector of the distance. So we track the trajectories of fluid particles and we study the behavior of r of t. Now, we want at this point to do something else. We want to be able to compare the behavior of this separation vector with other separation vectors such as this. So this is x plus r prime. And for that purpose, we need this matrix because this matrix gives a uniform way of treating these distances. So if this is image of this point x plus r, so by our definition, this point, position of this point is q of tx, this point is q of tx plus r, and so forth. So then we find that position of this particle is q of tx plus wr prime, and position of this particle is q of tx plus wr. So then you see that by studying the matrix W, we can compare the positions of different particles with respect to our reference particle at moment t. Okay, so this is another insight into this matrix. I see that there are significantly less participants than usual, and there are some people who came today. So I have, it's either the link is not so good, we use today a different link, or 4 hours are too much. Any of them, so okay, well, we continue. Okay, there's somebody else coming. All right, so then you want to study this matrix W, and as it stands, this problem looks kind of, well, it's not simple to understand how you approach this thing because you do not know. So I want to stress this again, that when we studied the Lyapunov exponent and generalized Lyapunov exponent, we were able to tell many things, not because we knew the structure of the turbulent flow. We do not know that structure. We were able to tell many things because of universal properties of behaviors of integrals of finite correlated random stationary processes. So there is kind of generalization of central limit theorem, which we call large deviations, with which we are able to describe things. So I really want that you think about it, that it's kind of remarkable that we speak of behavior of particles in turbulence at the same time not knowing anything about the flow, besides that it is finite correlated in time, which is certainly true. It was checked many times numerically, and there are no reasons whatsoever to think otherwise. So this is what makes this study at the same time very attractive, because you kind of tell something about something which you don't know. So it's kind of so for a long time, people thought that this type of problems are simply cannot be even thought about because we don't know statistics of turbulence, or how can we speak about statistics of particles in turbulence. And instead, people were all the time resorting to models, which were the most well-known are shell models of turbulence and Kraichner model of turbulence. And Kraichner model of turbulence assumes that this velocity field is in fact white noise in time. So I think we will have a chance to speak of that model as a realistic description of certain situations. However, up to the, I believe, 2000, up to the beginning of the year of 2002, 2001, people simply were considering for all quantitative statements V, which is white noise in time, and it was not considered possible to speak about turbulence at all. So you kind of get it for granted. I'm simply telling you this and that, and you cannot know the historical development of things. And it's good to know, because then you kind of appreciate more things which happened in recent times. So to treat this matrix, we introduce the singular value decomposition. And at this point, I want to explain to you how you can derive the singular value decomposition, because it's significant knowledge about matrices, and not only here. So I think it's worth that your knowledge and spending some time on this. So you are given some arbitrary so for the moment, let us consider it so singular value decomposition. So this is something which you can do for any matrix which is real or complex. The difference, as I told you, is that it's either the matrices are unitary or orthogonal. We do it for real matrices. So you consider any matrix W, of which the only thing which you know is that it is real. Okay, so we will introduce some more assumptions in a moment, but they will not be very restrictive, and they will certainly be true in our case. So when you think about this real matrix, well, it means that usually you can think in terms of eigenvalues, and eigenvectors, but eigenvalues are going to be, generally speaking, complex, and eigenvectors are going to be not orthogonal to each other. So it's not very, it's typically quite difficult to speak of eigenvalues and their evolution. And in fact, it's somewhat not thought about often. However, when we do this study of Lyapunov exponents, which is also applicable to any dynamical system, so at the same time that you are studying these things in turbulence, you are also studying chaos theory and things which appear there. There's no change whatsoever. It's simply the same formalism. So the theory of stability of chaotic systems, which studies the behavior of these Lyapunov exponents, in fact, it refers not to matrix W, but to matrix W transpose W. Okay, so you need to remember this, that in the end, our interest is quite often in this matrix, but W has significant physical information, as you see here. So it's somewhat beyond simple, well, not simple, straightforward Lyapunov stability analysis, as this is called. So you have this matrix, and then you can introduce another matrix, let me call it M, which we introduce in this way. So we write it as W, and then W transpose W to power minus 1/2. Okay, so what is it that we are doing? So this is definition. So I'll indicate it with these 3 lines. This is the usual notation for definitions. And what we do here is we simply tell, let us introduce this matrix and look at it. So I'm not going to pretend that I can give you any reason for considering this matrix. It's simply something which will bring you the result. You can look at it as a result of some, well, trying to do different things with this matrix W and composing different properties, and then in the end arriving at the idea to consider this matrix. So what this matrix is, you take matrix W transpose W, which is a real symmetric matrix, so it is diagonalizable, and you make an assumption that this matrix in fact has eigenvalues which are all positive definite. So otherwise the square root minus the square root will not be a well-defined property. So you assume that W transpose W can be written as N transpose matrix which is diagonal. We call it lambda square N, where lambda is the matrix whose eigenvalues are all positive definite. So we can write them as exponentials of some real numbers. And I'm giving you example, as usual, of 3 decays. It works in any dimension, and you want any dimension because it's the same thing you are using in the theory of chaos. And in fact, the study of this matrix in fluid mechanics brought some insights which were not known in theory of chaos. So in some way, fluid dynamicists were able to provide some information to those who worked in chaos for many years. And this is thanks to the fact that systems in fluid mechanics are random, and we worked on those systems more than people in chaos, well, and many other reasons. So we assume that this matrix rho, the eigenvalues are ordered. We can always do this. So we simply fix it in this way. And if you consider a case which is not degenerate, so if you have that eigenvalues are in fact all different, and this is the case which we can assume because we work with random flow, and in our case, probability of having the point which is degeneracy is simply 0. So we do have the right to assume that there is no degeneracy of this type. Then this matrix M is uniquely defined. Okay. So if there is degeneracy, of course, we can rotate within the eigenspace of degenerate eigenvalues, and N is not uniquely defined. So this is what we can do. And the remaining thing here would be to explain why the eigenvalues are all positive definite. And we will simply see it by continuity, because at time equals 0, all these rows are zeros, because lambda is unit matrix. I remind you that W obeys this equation with initial condition that W at t equals 0 is 1, is unit matrix. So initially all rows are zeros, and then by continuity you see that they never turn to minus infinity at any finite time, which equivalently means that all eigenvalues stay positive by continuity. All right, so what does this matrix give us? Well, we make simple observations. So I do need some more space, so let me, okay, this matrix is here, so I can erase this. Okay. So the observation which we make is that, in fact, this matrix M defined in this way is orthogonal. Now, how do we see it? It's in fact quite immediate.
Itzhak,
yes.
Careful, we don't see down there very well. Sometimes it crosses down the
Thank you.
area of the screen. Yeah. Thank you.
Okay. So the way to do it would be, it's funny, but well, so as a funny point, often when I hear this remark, I move the board and not the camera. It took me some time to move the camera. So this is only, well, I find it somewhat funny. All right. So you look at this thing and you see that if you take M transpose M, then this matrix is in fact unit matrix. Now, how you see it? Well, by definition, I think it's simpler to see M transpose. Of course, it's the same thing. So if you look at M transpose, you have that this is, by definition, W transpose W to power minus 1/2. And then you have the transpose, which would be W transpose W to power minus 1/2, because it's symmetric matrix, so its transpose is the same. We interchange the orders of operators and have W transpose here. Okay, so for some reason it's not very well seen, but this is a bit better. All right, so you see that when you multiply it with so this is W transpose W to power minus 1, and then you have that this is W minus 1, W minus 1 transpose, W transpose, and this is 1. Okay, so this is in fact orthogonal matrix. All right, so we got somewhere, and in fact we are almost there, because what remains to derive the singular value decomposition is to tell that in fact it remains to write W as M times W transpose W to power 1/2. Now this is again something which you see from the definition. If you multiply from the right with W transpose W to the power 1/2, you're left with W here. According to this representation, we can write it as M times N transpose lambda N. And finally, if you call this matrix R, which is product of two orthogonal matrices, so it's orthogonal by itself, you find this representation which we were using. Okay, so this is a derivation of singular value decomposition. It's for some reason I could not find it in the Wikipedia article on this, which is quite detailed because you use it a lot in numerical computations. It's one of the ways to think about matrices. But you can decompose them in this way, and it's something really to know of much use, but for some reason they don't provide this derivation. So I simply had to look at some papers which I knew. It's something old, and there is no reason why it would not be in that article, but it's not there. So
maybe you have to put it in the article. You have to edit Wikipedia, I think.
Well, I actually never did. Well,
first time.
All right. Well, in fact, I did make some effort some time ago, and I didn't comply with their strict rules, and I simply forgot about it because you need to write in a very special way so that they are all happy. There's thousands of people who kind of moderate, so it's really something. For this thing, please simply, it's one of the things to remember from the course because it's in fact also beyond the theory of turbulence. It's something really good. All right, so if you don't have any questions, then we return to the derivation and how we deal with this decomposition in our situation. All right, so given this decomposition, as I told you, you put it into the equation for the matrix W. You don't do anything spectacular. You take derivative of a product of matrices in this case as products of derivatives. And then you project, which means in this case that you use orthogonality in order to derive an equation of this form. So let me erase this. And so this is the equation which you get after you multiply this equation with R transpose on the left and with N transpose on the right. So you can introduce this matrix sigma tilde, which you can consider as simply matrix of derivatives of turbulent flow, which is considered not in the fixed basis, but in the moving basis, which is defined by this orthogonal matrix R. So it's simply rotated matrix of velocity gradients at each moment of time. It means that you have certain coordinate system, which is orthogonal coordinate system. You measure velocity gradients in that system, and you get the sigma tilde. All right, so
Itzhak, I do have one question. Sorry.
Yes, please.
Sometimes in the papers they refer to alignment. I'm talking about from the top of my mind, so maybe I'm not correct. But they talk about the eigenframe alignment with the rotational, I don't know, strain. I think it's the rotation of the strain or something like that. But the thing is they talk about the eigenframe, but I really don't follow very well what is the eigenframe. Is it related to this?
Okay, this is, I'm glad that we started speaking on this because indeed, if you go to papers, you can find things which are somewhat different. And in my mind, they are there because of historical reasons. So you have this frame. So there are, in some sense, there are two frames, okay, which you can see in the papers. So one frame is this frame of which is defined by this ellipsoid. So I can already erase this. So as we talked about at length, and you participated in that consideration, if you have infinitesimal ball in turbulent flow, it's going to be transformed into a pancake, usually. There are fluctuations, and there are some situations where this ellipsoid has completely different shapes, but the most probable situation is this pancake shape, which means that you have ellipsoid whose two axes grow exponentially at different rates, and the third axis shrinks exponentially to 0. So you have this structure, and of course this structure defines the orthogonal frame, which is defined by the axis of this ellipsoid. Okay, so this is very the same eigenframe as in fact definable with this matrix n. Okay, so this n is matrix of which performs rotation of vectors to this frame. Okay, so this is one of the frames. I think it's the most physically relevant frame because it really tells you where physical matter is going to point. So if you look at this ellipsoid, you can simply, by looking at it, see this frame. Okay. There is another frame which is more kind of, I would tell, imaginary or mathematical construct, which is this. So you look at matrix sigma, which is matrix of velocity gradients taken at the position of the fluid particle, which we are tracking in space. And you tell, well, this matrix sigma is, generally speaking, it's not symmetric. So its eigenvalues and eigenvectors are not that, the eigenvalues are probably complex. And of course, it has to do with vorticity. Because asymmetry of this matrix comes from vorticity, asymmetric component, antisymmetric sigma, as we discussed in one of the lectures, can be written as sum of, well, I don't want to erase this, I can erase this. So matrix sigma, which is simply local matrix of velocity gradients, as we already talked about it. I'll do it a bit faster. So you have matrix grad I vk, and there is a standard decomposition which you will find also in standard textbooks on fluid mechanics, such as bachelor book, that you can decompose it into the rate of strain matrix, which is simply the symmetric component of this matrix, and antisymmetric component. So rate of strain, of which we also talked on the last lecture, is simply symmetric component of this matrix. So it's grad I vk symmetrized, that is plus grad k vi divided by 2. So this is matrix which we call rate of strain. And then there is antisymmetric component. So this matrix is of course diagonalizable because it's a real symmetric matrix. And I think there's some blurring of the board from time to time. So if there's something happening, tell me. So then this component is what makes it its eigenvalues not real. And this component, in fact, up to some constant factor of 2, which must be somewhere, I don't want to care about it at this point, it's simply related to the vorticity of the flow. So if you introduce vorticity, which is typically designated by W as curl of velocity field, then AIK is this. So let me give you one more formula here, so that it's more clear that this is indeed this decomposition. So AIK is defined very similarly. However, you introduce here minus. So it's minus grad K of VI divided by 2 epsilon, which is, so you simply write grad I vk as grad I vk plus grad k vi divided by 2, and then plus grad IVK minus grad KVI divided by 2. So it's straightforward decomposition. And then you observe that this is all terms of this matrix which are not 0 are, you recognize in them components of curl. So then you can write it with the help of Levi-Civita tensor in this way, where W is the curl. So there's somewhere a factor of 2 here, which I never remember where it is, and always reconstruct when I need it. So this is the decomposition which people do, and then they tell, well, matrix A, the only thing which it does, it simply rotates, okay? Because local vorticity doesn't do anything to the vectors besides rotating them. So the whole strain comes from, well, the stretchings and contractions come from this matrix. So then you think that maybe there is some correlation between the axis of this ellipsoid and local axis of the strain matrix. Now, in reality, this never happens for various reasons. Some of them more obvious, some of them less obvious, but in reality, this thing behaves is something which accumulated information from the past, for starters. So it cannot be determined by the local in time eigenvalues or eigenvectors of rate of strain matrix. Another reason is that still there is, it's not meaningless quantity to consider, because you can think that there must be some correlation, because in the end, it's the strain which does the job. So this ellipsoid is going to point somewhere which is already correlated with local strain, because locally at this moment of time, strain indeed does something which is in accord with its eigenvectors. So it's either stretches along the eigendirection or contracts along another eigendirection. So you consider these two frames, and you usually what you do, you compare them. So you are interested to know how correlated they are. So you do find some positive correlations, which must be there, because simply you correlate something with something which is already there. Well, how to say it? Because the directions of this ellipsoid are already correlated, they kind of with a local strain. For times which are of order of correlation time of this strain, this ellipsoid was actually acted upon, was stretched by the local rate of strain. So there is some positive correlation. And then you measure it. I do not, I simply cannot tell you why it is useful. I'm not telling it's not useful. I'm telling that I don't understand why it is useful, because well, you want to know where this will, so in some sense, it's like this. You want to know where this ellipsoid will be pointing in terms of instantaneous flow. And the simple answer is that you cannot do this. So you do need some history. And then you kind of insist, you want to tell that, well, at least I want to have some idea of where it's going to point this ellipsoid. And then you do these correlations, and correlations are not so strong. There are correlations, but well, it's like you can tell that, well, it's pointing somewhere like this, okay? So you cannot really point the direction, but at least you can somehow tell something like, well, most probably somewhere here. So, okay, it is some information. It's up to you if you consider it as useful information. It's in some sense, there is some usage to it. So you do get some idea of the direction of this ellipsoid. However, it's rather vague. Okay, so this is about this question. If I responded, Emmanuel?
Yes, you respond. Thank you.
Okay.
Just in case it's helpful, I'm talking about this because I read some LES simulations, these large eddy simulations, they use for subgrid turbulence modeling. They use the strain rate and the gradient of a scalar, I think. And I know some papers, they are arguing that because there is no alignment of this ellipsoid and the strain, sometimes it's not a good, correct assumption. So I know there is higher order models for correcting this non-alignment. So this came from numerics of large eddy simulation.
We will speak about this direction. Yes, it's about that it's not very well correlated, so it's not so obvious why you want to do it, but well, you kind of, at least it's worth exploring how strongly they're correlated, and it's observed that they're not that strongly correlated. All right, so then let's go to this equation and how you deal with this equation. So for starters, you need to understand what is here what. So this is derivative of diagonal matrix. So of course it is diagonal. And then if you look at this, so let us use that this lambda is diagonal matrix. You can look in the appendix of that paper which I sent you, where this matrix R is in fact called M. However, that doesn't really matter. So what we are talking is about really construction of large deviations. So let me give you already here the concrete meaning to my words that fluid dynamicists were able to give something to theory of chaos. So people who study chaos, they want some kind of large deviations theorem for this W, and they did not have a complete formulation, and it was actually derived in the work on fluid mechanics, which where I was involved, so I know these things quite well. This is one of the contributions, but there was many more. We were never able, so there were in fact mathematical physicists who wanted to bring our results to mathematicians, and it's simply different directions of thought. So we continue doing our thing. I do see what they do in chaos. They look less what we do in fluid mechanics. However, please know that if you want at a certain point to study chaos, you will be able to use everything that you studied here and consult literature on fluid dynamics, and you might learn many things. So you use that lambda ik is exponential of rho I delta ik. So this is our definition of rho I. We defined it as square root of lengths of these ellipsoids. So this exponential of rho I, it's simply up to the radius epsilon. These are these are lengths of this axis of the ellipsoid. Okay, so this is epsilon times exponent of rho 1. So please do not keep the track of physical meaning of different quantities which appear here, because they're quite direct, in fact. So if you introduce it into this equation and you consider component ik of this equation, so what do you get? For starters, you need to observe that time derivative of matrix R. So let me write it. I want to introduce some notation before we do this consideration. So if you look at the paper, you will find there that this matrix R obeys the equation dtr equals R omega 2, where omega 2 is antisymmetric matrix. So the things which I'm telling you, people worked on them for many, many years, okay? So please, if it looks complicated, believe me that I'm telling you this, at least as far as I know, in the simplest possible way. It's simply unavoidable to do all this type of calculations. All right, so you write dtr in this way, and this matrix, this is the most general evolution which you can write for matrix which is orthogonal. Now, how do you see it? You look at this, so this is something which you saw. I unfortunately had to erase it. So you start with the fact that R is orthogonal matrix, which means that this time derivative as time derivative of unit matrix is 0. So then you get from this that R transpose dtr plus dtr transpose times R must be 0. Equivalently, you can tell that matrix omega 2, well, let's, I need to see the screen, if you can see the board there. Okay, so I will at this point erase the derivation of singular value decomposition. Okay, so if you look at these equations, you can define the matrix omega 2 as, so I'm deriving at this point this equation. So you start with this observation. You understand that R is some orthogonal matrix. So far, we don't use anything more. And then if we define R transpose dtr as matrix which we call omega 2, then you see from this equation that in fact this term is its transpose. So this equation tells us that omega 2 plus omega 2 transpose is 0. Okay? So these are often things which you learn when you study at depth rigid body dynamics. So at certain point, so those of you who did it, you will simply recognize some things here. So this equation tells us that this matrix must be antisymmetric, because this, when you take transpose of this term, you get dtr transpose here, and then R transpose is R. So this is the meaning of this equation, and this is what I wrote to you here. So this is simply using that R is orthogonal matrix. It doesn't use any equation, okay? It's, so to say, must be like that with some matrix omega 2, and what this matrix omega 2 is what the dynamics determines. Now, the same thing you can do for matrix which is n, okay? So for matrix n, we define it a bit differently. So we start with the same equation. So you saw this equation, so let us do it a bit. So in this case, you can do it a bit differently. So you write that n transpose is 0. And then that gives you that n dt n transpose so you can, of course, do it a bit differently, simply kind of tell them that let's consider instead of R transpose of R, but let me show to you these things in detail. So dt n transpose plus dt n times n transpose is 0. So the same thing, however, this time we define the matrix differently. We define, in this case, so we define omega 1 as dtn n transpose. Now then again, you look at this equation and you find that this matrix omega 1 is again antisymmetric. So you find that omega 1 plus omega 1 transpose is antisymmetric. And then this equation tells you that time derivative of n can be written in this form. dtn is omega 1 times n. where omega-1 is again matrix, which is antisymmetric. Okay, so it's a kind of simple considerations. So if you write it in this way, where the evolution matrix omega is to the right, then this matrix must be antisymmetric. Or you can write it with evolution matrix which stands to the left. It's dictated by the what is more useful in the calculations, but not by something. So of course, and also base an equation of this sort with some other antisymmetric matrix. So this is our definitions, okay? We can always introduce these definitions, and then we're going to use them here. So you rewrite this equation in this form. So by definition, this matrix is omega-2. So we have omega-2 times lambda plus dt lambda. Now this matrix by definition is omega-1, so we have plus lambda omega-1 equals sigma tilde, this rotated matrix of velocity gradients in rotated frame, times lambda. Okay. So this is the equation in which we want to put the knowledge. So far we used that matrices R and N in this equation are orthogonal. At this point, we want to use that this matrix is diagonal. So I will erase this. When I erase, it's time to ask questions if you have any. Okay. So we use this. We take ik component of this equation. So we find that omega-2 IL times lambda LK, but lambda LK is exponent rho L delta LK. And I remind, we sum over all repeated indices in the equations. Then you have plus rho I dot exponential of rho I delta IK. Okay. And then we have the last term, which is plus exponential of rho I. And then you have delta IL omega-1 LK, but that is the same as omega-1 IL IK. Okay, and this all is equal to sigma tilde IL multiplying exponential of rho L delta LK. Okay, so it's straightforward, a bit cumbersome, but straightforward. Then, of course, here you can perform the summation. So when you sum over L, because of this delta, this L becomes K. So you find that this is rho K. So the only thing in these calculations is not to get confused about the indices, and this is what I will make an effort not to do on the board. So this is omega-2 IK. This is already IK. And then, so what remains here, this is okay. And finally here, summation over L makes it exponent of rho K and K here. Okay, so we used everything which we had about these matrices, that these matrices are orthogonal, and this is diagonal. At this point, what remains is simply to observe what we have in this equation. So for starters, you see that if you consider I equals K, then because this matrix is antisymmetric, on the diagonal you have 0. Okay? And the same is true about this matrix. So for I equals K, these two terms do not contribute, and this gives us the equation that rho I dot, so you take k equals I. So if k equals I, you can, these exponential terms disappear, and you're left with sigma tilde I. So this is when you set k equals I. All right. So this starts to look good. Why? Because you see that these random noises, rows, which are kind of hidden inside this matrix W, in fact obey equation which looks already as similar to what we had previously when we considered logarithm of distance between two particles, because its evolution is driven by some noise. So we hope that if we integrate this equation over time, then at large times, these rho i's will be kind of sums of large number of independent random variables, and we will be able to use this large deviations form of the distribution, which we talked about, and we will again reiterate. So I am making effort to speak of the same things from different angles so that they learn better. So this is already good. However, if you look at it, you see that it's not obvious yet that this sigma tilde is completely kind of independent of these rows as we want, because the sigma tilde involves R, and it's not obvious yet that this R matrix is independent, its evolution is independent of these rows. So we need to make more steps here, and of course we do them. So we write down, we now consider components which have k which is different from I.
Itzhak, can I ask a question?
Yes, of course.
Why does this equation has to hold for every k individually, not for the sum? Because you're picking out now one contribution of the sum and saying it holds for these contributions.
Because it's not a sum. So here, so we have this matrix equation. So this matrix must be equal to this matrix. Both of them are in our case, 3 by 3 matrices. So matrix equation means that element ik of this matrix equals element ik of this matrix.
Yeah, I got it. Thanks.
All right, you're welcome. All right, so then let's see if we make a break or one more step. What is your preference? No preference. Okay, so let me make some more steps, and then at 12 we'll take it. Well, at 11. All right, so at 11, which is Spanish and German time, and also Russian time, and there is Chinese time, which I think at the moment is a bit late. By the way, I would be glad to know where you are from. Some of you I know, some of you I can guess, but not all. All right, so we look at diagonal elements of this matrix equality. Now we look at non-diagonal elements. You see that immediately this will not contribute there. So non-diagonal elements tell us this, that omega 2 ik exponent of rho I, exponent of rho k, plus omega 1 ik. So here we take k, which is different from I. So this term is 0, plus omega 1 ik exponential of rho I equals sigma tilde ik exponential of rho k. And what remains is to get out of this equation, we want to get omega 2 and omega 1. So we want to solve this equation with respect to these matrices, and then we will have the evolution of matrices R, which is R omega 2 and matrix n, which is omega 1 n. Okay, so all right, thank you, Francesca. And there's somebody else, and Ilham, thank you. All right, so how we extract these matrices we'll talk after the break. In the remaining minute, maybe you can have you can ask some questions about what we are doing. It's a bit mathematical calculation, not that difficult, but tedious and demands a lot of care. Any questions on that? All right, then we take a 15 minutes break and then continue. All right, we continue. Thanks for those who told me where they are from. I think that the rest are from Spain and besides the countries, and that's it. All right. So we look at these equations and we want to extract omega 2 and omega 1 in order to complete our set of equations. So the first equation of our set is this, in this sense that we want to get out of this equation on W as a whole object, we want to get separate equations for R, lambda, and N. And this is the equation on lambda because lambda is composed of exponentials of these rho i's. All right, so what do we do with this equation in order to get out of it these matrices, omegas? These omegas define, of course, some local rotations. Any antisymmetric matrix defines a rotation. So, as you can guess, it has some physics behind it, and indeed it does. We will maybe not speak about it too much, but there is all these matrices have physical meaning. So to do this, you want to use somehow that they are antisymmetric. So what you do is you write the same equation interchanging k and I. So you have omega 2 ki exponential rho I plus omega 1 ki exponential of rho k equals sigma tilde ki exponential rho I. So this is not new equation, it's simply we relabel k as I and I as k, okay? Now, the remaining thing is this. You recall that these matrices are antisymmetric. So if you can isolate from this equation omega 1 ik and from this equation omega 1 ki and you sum the equation, then omega 1 will disappear, leaving us with omega 2. Okay, and similarly you can do with omega to eliminate and get omega 1. So let us do this. I do it in detail so you can see every step of this calculation and see how these things work. So you multiply the first equation with exponential of minus rho I. What you get then is omega 2 ik exponent rho k minus rho I plus omega 1 ik sigma equals sigma tilde ik exponent rho k minus rho I. And with this equation, you multiply it with exponent of minus rho k. So you find omega 2 ki exponential of rho I minus rho k. And then this gives you plus omega 1 ki. And this gives you sigma tilde ki exponential rho I minus rho k. So we multiplied this equation with exponent minus rho I and found this equation. And this equation we multiplied it with exponent minus rho k and get this equation. So the next thing to do is to sum these equations and use that sum of omega 1 ik plus omega 1 ki is 0. So when you do this, and so you can, you need to decide which of the elements of omega 2 you want to fix. So I'll do it as in the paper. So omega 2 ik, well, in fact, let's fix simply omega 2 ik. So when you sum these equations and you use that omega 2 ki is minus omega 2 ik, you find omega 2 ik times, from here we get exponent rho k minus rho I, and from here we get minus exponent rho I minus rho k. This, as we, well, by definition, so to say, is 0. This is where we're heading for. And finally, we have this sum, which is sigma tilde ik exponent of rho k minus rho I plus sigma tilde ki exponent rho I minus rho k. So the end result is that, so from here you can derive, well, what do I do here? We need to extract this and that. All right, so I think that you divided by, so you multiplied by exponent rho k plus rho I, okay? Yes, I think so. So you multiply this equation by exponential of rho k plus rho I, and then of course divide by this thing to get omega 2 ik, and you find that omega 2 ik is, so if you multiply this with exponent rho k plus rho I, you have that this is sigma tilde ik times exponent of twice rho k. Here you get plus, let's not write that well, let's see if this, oh, okay, plus sigma tilde ki exponent twice rho I, and we need to divide with what we have here, which is exponent of twice rho k plus minus exponent of twice rho I. Okay, that is compared with the paper. Sigma tilde ik exponent to rho k plus sigma tilde ki exponent to rho I exponent to, okay, good. All right, so this is derivation of the equation from the paper after A2. So I remind you, this is we're deriving equations which are found in this paper on spectra of turbulence and polymer solutions, which I sent you in the appendix. So then you do the same procedure for omega 2, sorry, for omega 1, and it's simply you do the same things, okay? You instead you isolate omega 2 ki and omega 2 ik, you sum the equations, and I'll give you the end result because it will be not difficult for you to repeat these things. So you find that omega 1 ik is sigma tilde ik plus sigma tilde ki divided by twice hyperbolic sine of rho I minus rho k. Now all these equations hold for k which is different from I. So for k which is equal to I, we simply have 0. So at I equals k, these terms will become infinite. So you do not use these terms there. And finally, we are ready to write our equations. Okay. So we have this equation that dt rho I is sigma tilde II, where sigma tilde is R transpose sigma R. Then we have the equation that dt n is omega 1n, and dt R is R omega 2. All right, so what you have on the board, erase this, and let us rename it as, well, I haven't yet spoken. So this is, let's say, deformation tensor. Well, in fact, it's not deformation tensor because that is often called W transpose W. So this is Jacobi matrix. All right, so this derivation is completely general in the sense that whenever you have any kind of flow, it can be turbulent flow, it can be flow in the phase space of any chaotic system, you are able to write these equations for a matrix which specifies the small scale structure of the transformation of space, which is done by the flow. And when we speak of transformation done by the flow, what I mean is that you have so you have the fluid at t equals 0, and it is transported to new positions at time t by the flow. And this is kind of, you can think of it as transformation of space or motion of space. And small scale structure of this motion of space is described by this matrix W. And for each initial point x, you can write these equations. So these equations as they stand do not yet allow you to get large deviation theory, because you see that evolution of these rows depends on R, and seemingly because evolution of R, it depends on omega 2, evolution and omega 2 depends on rho, then these are still coupled equations. So we want to compare these equations with the equation which we wrote previously, that ddt of logarithm of distance is this logarithmic stretching rate, where n is evolving according to this equation. So we want to compare these equations. So there we could tell immediately, without any simplifications, that evolution logarithmic derivative of distance does not depend on distance itself. It's some noise which is kind of out from the viewpoint of this logarithm of R variable. It is outside noise, external noise, which is defined by matrix sigma, and by n, which is defined by sigma. So that allowed us to get this large deviation theory for this R variable, and to get Lyapunov exponent and everything else which we started. Now here it's not completely the same. However, we are in fact one step away from getting a formulation which is very similar to this. The only thing which you need to think about is that you typically, these raw variables grow with time, and the rates of growth are, in cases which are not degenerate, are simply different. So if you consider, say, typical fluctuation, so at large times, we are given by the Oscillator's theorem that rho I must be lambda I. So if you assume self-consistently that at large times you have rho 1, which is much larger than rho 2, much larger than rho 3, which is something which would be guaranteed by this behavior if lambda 1 is larger than lambda 2, larger than lambda 3. So if there is no degeneracy, then at large times this variable's rho will be vastly different. And in physical terms, it means that all aspect ratios of this pancake grow in time exponentially, and you have very disparate lengths of this axis. So that is somehow must be inside these equations unless we consider some case which is degenerate, where for some reason some axis of this ellipsoid grow in the same way, which would correspond to degenerate Lyapunov spectrum. So in this case, you get immediately that these equations become very simple. So sigma tilde is something which is has constant magnitude, because in the end it's the same matrix sigma, which is stationary and it doesn't depend on time. It is simply rotated, so rotation doesn't change the magnitude of this matrix. So this term is kind of time-independent process, stationary process with stationary fluctuations of limited magnitude. However, when you look at the denominator, and of course you need to see, I didn't tell this, these expressions are explicitly antisymmetric. So if you interchange I and k, you interchange sign. So if you look at the denominator, because rho I and rho k grow, so the difference between them grows exponentially, then this matrix, in fact, decreases exponentially to 0. So let me, well, how I just write it. Okay, so this is something which is of order. Okay, I will erase this thing. So if, say, lambda I greater than lambda k, then it's so it's of order of exponential modulus lambda I minus lambda k times with minus. Okay, so the denominator will be determined by the exponentially growing term, which means that denominator is exponentially growing function of time, which means that when we divide it by that, we get this. All right, so this is already something good, because you see that it actually gives you immediate understanding into the claim of Oscillator's theorem, because you see that matrix n becomes, at large times, becomes simply constant, because its derivative tends exponentially to 0. So we get the implication that n of t is approximately constant at time which goes to infinity. And this is what we claimed. So Oscillator's theorem told us that limit as time goes to infinity of logarithm of positive definite symmetric matrix W transpose W divided by 2t is n some fixed matrix n transpose. So let me designate this matrix by n infinity so that we can connect these things. So this is a constant. So this matrix has a finite limit. And here you have lambda 1, lambda 2, lambda 3, 0, and times n. Okay, so we reproduce this claim of Oscillator's theorem that the matrix which diagonalizes this limiting matrix is in fact has a finite limit and at time going to infinity. So this is already something. And the next step which we see is that we observe that these terms are in fact become, by the same token, they become independent of rows. Why? Because either so we have in all cases, because in this situation I is not equal to k, so you have that either exponential, so one of these exponents is much larger than the other. Okay, so either this is much larger than this, or this is much larger than that. In that case, both, let's say that this is exponent of 2 rho I is much larger than exponent of 2 rho k. Then you can neglect this term in the numerator, and you also can neglect this term in the denominator. And then when you consider the ratio of numerator and denominator, this term disappears. So the dependence on the row disappears. The same thing is true if this term is much larger, if this exponent is much larger than this, then in the numerator this disappears, and denominator this disappears, and again the ratio is independent of rows. So this is a conclusion which you can explicitly write this thing. So let me do it. So you have that. Let's see what I can erase here. So let us assume that we consider omega 2 at I, which is larger than k. Okay, then by our definition, this term is negligible. And this term is negligible because k has smaller index, and according to our condition, it grows faster. So the whole thing becomes sigma tilde ik. And in the opposite case, where I is smaller than k, you can use antisymmetry to tell that this is minus sigma tilde ik. So it is independent of rho. In other words, let me write this down. Matrix R at large times evolves independently of rho I. All right, so this is our conclusion, and it means that when we consider this equation, these sigma tildes are kind of noises with given statistics. And this is what we need in order to get the situation where we can use large deviations theorems. So before I give you the result, please tell me if this derivation was understood. It's lengthy, but it's straightforward. So I hope that you could understand it and grasp how it's done. So any remarks, questions? All right. So we are actually there. We reached quite complete description of evolution of small volumes of the fluid, which you will be able, hopefully, to use in your work, or simply will somehow, well, this knowledge will be useful to you in some other way. So we find that, so let us consider dimension which is 3, which is most usual application in fluid mechanics. So then we necessarily have that rho 1 plus rho 2 plus rho 3 is 0. And this is consequence of incompressibility, which implies that Jacobian, which is determinant of this matrix W, is 1. So the only thing which we need is to describe the distribution of these rows. And to describe that, we can consider then this representation. So we don't need to consider row 3 because row 3 is simply minus row 1 minus row 2. And then for row 1 at time t, because initially matrix W is unit matrix, so all rows initially are zeros. So row 1 at time t is equal to integral from 0 to t, sigma tilde I t prime, sigma 1 1 t prime dt prime, row 2 of t equals integral from 0 to t, sigma tilde to 2 t prime dt prime. Okay, so what you have from this is representation which is true at all times. However, when times are large, you know that these sigma tildes are in fact independent of rows. So you can neglect contribution of finite time into these integrals, where there was still some dependence. And then you can consider effectively that all these sigma tildes are already stationary processes, which you get by solving equation on R. So you have an equation on R, which is dtr equals R omega 2, where roughly speaking, omega 2 is sigma tilde. Okay, so this is the evolution which you have, and when you solve it, you get some stationary statistics of R, because sigma is stationary, and stationary statistics as a consequence of sigma tilde. So these are some stationary random processes which you integrate, and then you can claim, using the same cumulant expansion theorem, that moments of exponentials have behavior which is exponential in time. So you can claim that, for instance, exponential of k rho 1 at time t plus L rho 2 at time t on average has behavior which is some gamma tilde of k and L times t. Okay, so you use for that the same cumulant expansion theorem, which you apply this time to this. So you consider this whole thing as one scalar random variable. You apply cumulant expansion theorem, you open the brackets, you observe that each cumulant is proportional to time t, and as a consequence, you find that logarithm. So I remind that our function gamma tilde is always kind of cumulant expansion function, generating function, and the theorem tells us that logarithm of this average is series in cumulants. Each cumulant, because the noises have finite correlation time, are proportional to time t, which implies that at large times this has exponential behavior in time. There's absolutely no difference from what we did before, only a bit Camperson notation, because you have two noises and not one. So are there any, do you need me to repeat those considerations, or we can proceed? Who does not understand that the behavior at large times is going to be exponential in time? Who understands? Okay, let me. So we are 17 people here, assuming that I understand. Okay, thank you. All right, this is a relief. This some of you understand, and I can hope that others understand more or less. Ilham, do you want to comment? Because I think that according to what you wrote, for you it must be more difficult. Okay, so last time there was a problem with unmuting. Okay, thank you. All right, so then I hope I did not touch you with my request to react to what I've done, because, well, you simply need to understand that telling something in front of people which you don't see is, it's not that there's kind of no connection to the class when you do online lectures, there is, but you still need to hear from time to time where you are. So this is the derivation we get here, and the rest is already application of this large deviations theorem, which I told you many times. So I will again reiterate this thing, because you need to hear things lots of times before they get absorbed. One thing which I want to tell here is that so when I tell that fluid dynamicists were able to contribute theory of chaos in this respect, it means this, that heuristically people who worked on chaos did know that this type of quantities, which they introduced in a bit different language, so they didn't have these definitions of Rho, but okay, they did in fact. From W transpose W, they defined these Rhos in more or less the same way. So they did know that there must be some kind of exponential behavior. However, they did not have any consistent way, any insight to prove this thing, when it works, when it doesn't work. And as a result, they were not able, for instance, to produce the, to have any insight into this function. So our approach, which allows you to write concretely in terms of definite properties of the flow, so at least in principle, this allows you numerically to obtain this function gamma of KL from studies of statistics of this stationary matrix. And this is something which is, thank you. So this is something which you need to have in mind, that in principle, you go to simulation, you produce straightforwardly matrix R starting from matrix sigma, which is straightforward to find. You write down this sigma tilde, and you study its diagonal components. And that's it. You can get from that. So you study the adjoint statistics, the cross correlations between diagonal elements of this matrix. So by compressibility, I remind you the trace of this matrix is 0. So sigma tilde 1, 1 plus sigma tilde 2, 2 plus sigma tilde 3, 3 is 0. And then you can get anything you want from this. So you can more or less do it in the same way as you do with derived generalized Lyapunov exponent. And if you look at paper by Manifold and Johnson, which I sent you, you will see that they do it a bit differently, though similarly. And I do think that it would be good to do it in this way, because I think it kind of saves some effort and allows to get some quite detailed results. So let us do the last calculation here, which is, okay, I can already erase this, that you can, so I remind you that if moments of some variable, so this implies that probability distribution function of ρ1, ρ2, ρ3 can be written as, so in the leading order, this exponential and time dependence is given by some large deviations function, which depends this time on two variables. So you will see that you need to rescale by time. So if you want, okay, let me maybe formulate it in terms of finite time Lyapunov's exponent to have consistent notation. So finite time Lyapunov exponents are then defined as lambda I as a function of time, which is rho I of t divided by t, which is the same as 1 over t, integral from 0 to t, sigma tilde I t prime dt prime. Okay. Now I'll give you one more application, which I think is kind of interesting, and then we'll take a break. So you have that this sigma tilde I defines for you this finite time Lyapunov exponents, which in simple terms means that you consider this ellipsoid into which the ball evolved, and the axes are in this notation given by exponent time times lambda I of t. So lambda I of t are kind of effective growth rates, which you would write at time t. So in the end, we know that these growth rates by themselves change, and in the limit of infinite time for almost all initial conditions, which is another way to tell that for initial conditions up to some set which has 0 volume and 3 dimensions. This is again something which we learned already. So at finite times, this lambda I of t are some quantities which are different from their infinite time limits. And infinite time limits are this spectrum of Lyapunov exponents, which we talked about what it is at turbulence, that lambda 2 is something like quarter of lambda 1, and lambda 3 is then minus 5 lambda 1 over 4 by incompressibility. So you have these things, and then if you write probability density function in terms of these variables, it takes, according to the same theorems which we studied, it has this form. Now, I kind of a bit reluctant in writing it in this way because you can get confused about lambda ones as functions of time and lambda ones which are in the spectrum. So let us agree that when I speak of limiting values of Lyapunov exponents, I will introduce infinity in the superscript so that there is no confusion. And then you have that there is some kind of large deviations function, which again has very simple meaning. So I will remind it to you in a moment. You can tell it, but I don't want to ask you about it because you simply might not guess what I want here. So I will tell it. And in the end, you have this condition of incompressibility, which is delta lambda 1 plus lambda 2 plus lambda 3. Okay, so this is, so to say, a very detailed description of statistics of Jacobi matrix. So you need to think about it. So you have some space which flows, so there is some flow defined in that space. Neighborhood of each, a small neighborhood of each point, initial point x is transformed, say balls are transformed into these ellipsoids. We know what these ellipsoids, what their axes are. So their axes have statistics, which is defined by the fact that when you pass from one initial condition to another, the infinitesimal ball around that new initial condition will evolve into a different ellipsoid. So if you want to describe fraction of space where the axis will be given by some lambda I of t, which are equal to some given lambda i's, you have this probability distribution function, which tells you fraction of initial space, which is where initial conditions bring you ellipsoids with these axes. So as time increases, we must get this, according to the ergodic theorem to which we reduce this. So we reduce this thing. So lambda I at time t, given by this formula, according to the already usual ergodic theorem. So the whole theorem is called multiplicative ergodic theorem. And the whole thing is that you reduce multiplicative noise to additive noise, as here. This is what all these transformations which we did lately, what they do. So you see from this that limit as time goes to infinity of lambda I t is lambda I infinity in these notations, which we agreed upon. So at least I propose them. I cannot tell that we agreed upon this because I cannot hear you, unfortunately. So when I arrange some things on the board, whenever you have, you want to ask me anything, please do so. All right, so these are the limits, which means that S of lambda 1, you can show it in the same way as in our discussion of large deviations function or Kramer's function or entropy function, that this is a function which is greater or equal 0, and it has unique 0, which is the minimum at lambda I equals lambda I infinity. So what this tells is simply a different form of Oscillator's theorem, which tells you that if these lambda 1s are different from their infinite time limits, then the fraction of initial conditions for which we get these values lambda 1 and lambda 2 decreases exponentially in time with the exponent which is given by this large deviation function, and only if lambda 1 and lambda 2 are equal to the infinite time limits, then this S vanishes, which guarantees to us that in the limit of infinite times, probability density function of lambda 1, lambda 2, lambda 3 becomes delta of lambda 1 minus lambda 1 infinity, delta of lambda 2 minus lambda 2 infinity, and delta of lambda 1 plus lambda 2 plus lambda 3. So this is direct consequence. So as you can see, this is very simple to see. We spoke about it, but I repeat it in a bit different way. So you have a function whose integral over lambda i's is 1, and which in the limit of t going to infinity vanishes everywhere, but at a point which is lambda equals lambda 1 infinity and lambda 2 equals lambda 2 infinity. And this by definition is delta function concentrated at these points, because delta function is a function which is 0 outside certain point in space, and its integral over the whole space is 1. So this is how you see that this is really equality. Okay, so this is a probabilistic form of Oscillator's theorem, because probability here is defined with respect to the average over initial conditions, and this is equivalent to what Oscillators told us, because Oscillators tells us that these limits hold up to some points which have 0 volume, but 0 volume in our definition of probability as fraction of space of certain value is the same as 0 probability. Okay, so this is completely equivalent to Oscillator's theorem, and in some sense, not in some sense, it gives you actually derivation of the Oscillator's theorem for non-degenerate case where these lambdas are different, because it relied on assumption that this axis of the lengths of the axis of the ellipsoid are becoming disparately separated at large times. All right, so I hope that this whole thing was understood, and I want to give you a curious application, which in fact is little known, and it's I find it very useful. So you saw that if we want to derive lambda 1, we don't really need to solve matrix equation. So for lambda 1, we could get this representation that you only needed to solve dn dt equals sigma n minus n sigma n times n, and then lambda 1 is average of n sigma n. So you don't need to get lambda 1, you don't need to get into some matrix equations to solve them. You can solve this vector equation, and that's very good. It's much simpler. It's moreover, it's equation on unit vector, so there are only 2 degrees of freedom. So for instance, introducing angles of spherical coordinates, you can write equation on theta and phi of this vector. And from that, you can easily, or more or less easily, get the evolution. And then from that evolution, you fix this n, you multiply sigma from both sides with n, and you are done. So you average over time, and this is lambda 1. So this is the shortest way to get lambda 1. It's of course shorter than to get this matrix equation and solve it. Simply much less degrees of freedom. So you could wonder if you could get the same representation with vectors for other Lyapunov exponents. And the truth is that yes, you can do it. And for that purpose, you can actually, well, I'll give you the result and then we take 15 minutes break and then we continue. So the result is this, that you can get lambda, let's erase this. So lambda 3 can be obtained in a very similar way. You consider dm dt, and the only difference is that instead of using matrix sigma, you use matrix which is minus sigma transpose. So I will write it in a way which makes it explicit. And then minus lambda 3 is average of n minus sigma transpose n. So this is a representation which is less known, and it's again very useful because you can get lambda 1 from this representation, you can get lambda 3 from this representation, and because total sum of lambdas is 0, this gives you the whole spectrum of Lyapunov exponents of turbulence. So we take 15 minutes break, and after the break, I'll show you how
Itzhak,
we derive.
give me a second.
Yes.
Can you write it again with another marker? I cannot see very well the formulas you wrote.
Oh, okay. All right, so let's. Okay, so we have this representation for lambda 1, and for lambda 3, I will show to you that there is very similar. No, this is not a good red color. One moment. Okay. So dm. So instead, it's of course different n. So let's call it p. So dp dt equals minus sigma. So the only thing which you do is instead of sigma, you use here minus sigma transpose. So if in some simulation minus sigma transpose p, you need to do calculation of, so say you want to get the best measurement of Lyapunov exponents up to date and publish it. So determine lambda 1 from this, determine lambda 3, what I'm showing you at this moment, and this would be the way which will save you lots of numerical work, and hopefully you will indeed be able to produce good numerical results. So this is this average. And so I on purpose write it not simplifying things as I could, so that you see that the only thing which you need to get lambda 3 is to change sigma with minus sigma transpose in these equations. All right, so Imanol, is it, this time it's okay? I hope it's visible, and we take a break.
Thanks.
All right, we continue, and my purpose would be to show to you that this representation which we derived, it's really something very useful, and I would want to show to you, in fact, more than only that you can get lambda 3 in this way. I also would want to show to you that you can get in a much more robust way with significantly less number of degrees of freedom, this whole function of large deviations. So this way of doing computations was not used because, well, I did not publish it separately. you can only find a remark in the appendix of my paper of 1999, in fact, about this. So it's not widely known, and then people simply do the matrices, which is okay as long as you have really high power. But I do think that you can get more precision by solving simultaneously this and this system and considering joint statistics of the noises which you get in this way. You can actually derive this function much more efficiently. I think it's, so what I'm going to tell you is minimal description. How you get it, you start from actually treating, looking at this representation, which I showed to you, as a way to calculate things and not simply a way to prove the large deviations theorem. So for this, you need really kind of so let me write it instead of speaking. Okay, so let's call it minimal way to statistics of finite time Lyapunov exponents. Okay, so you start with our definition. So our definition is that lambda, let's make it so lambda I of t is defined as rho I of t, and we can always write it as integral from 0 to t sigma tilde I t prime dt prime, where sigma tilde is defined as R transpose sigma R, where R is orthogonal matrix. And this orthogonal matrix evolves according to the equation that dtr is R omega 2, where omega 2 is, let me simply write it down. So at large times, we consider, we assume the limit of large times with no loss, because we are from the very beginning interested in the limit of large times. So we can assume that rho 1 of t is much larger than rho 2 of t, much larger than rho 3 of t. And then this omega 2 is reduced to simple form, which is this. So if you consider, let me consider the case where, let's assume that k larger than I. Okay, so if k is larger than I, then from what from the expressions which you had, you have that well, omega, completely. So omega 2 I k for k which is larger than I. So then you can neglect exponent of 2 rho k. This is minus sigma tilde ki. And the other way around, if k is smaller than I, then this is, you can get it either from antisymmetry, or I want to check it directly from the formula. So I'm looking at the paper so that to be certain that there is no mistake. So if k is smaller than I, then it is plus sigma tilde ik. So this is okay. So this is minus ik. All right, so this is these are our formulas. These formulas are already kind of concentrated so that you can forget about rotational degree of freedom, which was n. It's not present here at all. And you can also forget about the initial evolution of R, which was not determined by these equations. These are equations which you need to study statistics of lengths of this ellipsoid, okay, into which the volumes evolve. So what you need is so to start with, you can consider this question. So, okay, I look at this. This is this formalism which we studied. At the same time, I did not forget that I spent considerable time on this course. And previously, I had that representation that lambda, we had lambda 1 as average of n sigma n, where n was unit vector which obeyed this equation that dn dt is sigma n minus n sigma n. And of course, because I thought of this and I wanted, and I spent so much time on this, I want to get some connection between things which I study in order to use them. So somehow this representation of lambda 1 must be inside this representation of lambda 1, because this representation of lambda 1 tells us that lambda 1 is average of sigma tilde 1, 1. By the same token as we did it before, because in the limit, this is time average, and time average is assumed by ergodicity to be equal to the average of initial conditions. So if there is any, so somehow I must be able to pass from here, okay? So how do I do it? So I need to look close at the equations and see if really it is there. So, well, you look at it and it doesn't look from very beginning very similar, but then you kind of come down and you start looking at things in detail, which means usually simply look at definitions, what you are studying, and consistently pass from one line of calculations to another. And if you don't make mistakes on the way, usually you are fine after that. So what we need to do is, because lambda 1 is sigma tilde 1, 1, and of course I didn't forget about sigma tilde 3, 3, what I want to show to you is first how we reproduce previous result, and then we get a new result. So we concentrate on sigma tilde 1, 1. And for that, we simply write, so sigma tilde 1, 1 is R transpose 1k sigma k L R L 1. So by definition. So then I can write it, of course, as sigma k L R k1 R L 1. Okay, this starts already to look similar, because R is diagonal matrix, which means that, so R transpose R, if you look at its elements, so this is sum of, let's look at element ik. So this is R transpose. I on purpose write everything in detail so that you will be able to do these calculations. For some of you, it might be boring, but at least, well, I do need to give all these details. So you have that this is R transpose I P R P K. So by definition, and this is sum of P. And then this is R I P R R P R P I R P I R pk, and this is delta ik. So sometimes I write summation, sometimes I don't. So this is this, and you want to get that. So you need to get, so instead, if you consider R transpose, so if you change to this, and you get that this is RIP, RKP, which is also delta IK. In other words, what this identity tells you is, in fact, that if you take, okay, the other way around, of course. Okay, never mind. So what I want to tell in the end is a simple thing, that if you consider vector Fi, which you define as Ri1, that this is a normal vector with unit magnitude. Okay, so so I want to show to you that Ri1 is 1. And that you can get from any of these, in fact, the previous one, but okay. So this is 1, okay? I don't think there's a problem, it's the previous identity which I needed. Okay, so this is starting to look very similar, and it of course gives you an idea to call this vector in the same way, to call it Fi. So you see that you get similar representation. So if you define the vector in this way, it is a unit vector because R is orthogonal, and you find that this is n sigma n. So what remains is to show that this n will actually obey this equation, and then you will see the equivalence. Okay, so let us look at the equation for n. So n is defined in this way, and what we must do, we must consider its time derivative. So we consider d dt of ni, which is by definition d dt of ri1, and then we use this equation. So this is rik omega 2 k1, and repeated indices are summed. Okay. So then you use this representation because k equals 1 is 0. You can write it as sum over k's which are in fact larger than 1. So this is this case. Okay. So this is. So let us write it in this form. Okay, so let's go step by step. So I want to skip here, but okay, let's do it step by step. So this is minus rik sigma tilde k1. Okay. 1k. So you need to be quite careful in these calculations about indices. Okay, so because this is the case where last index, no, the other way around. Okay, so the last index here is smaller than the former, than the first index. So we are in the case of this, where I is greater than k. So we need to use that this is sigma tilde with the same indices k1, okay? And then it's plus, okay? However, the summation here goes only over k, which is larger than 1, because for k equals 1, this is 0. Okay, so far so good. So then we can rewrite it as RIK sigma tilde k1, already without this limitation that k must be larger than 1. And then we need to take this term out. So minus RI1 sigma tilde 1, 1. And you see that you start to get something very similar to the evolution of n. So it gives you, okay, somewhere I mixed the indices. So this is, let's see. I don't know, it's okay. All right. So we need to recall the definition. So this is, okay, I'll erase this. Okay, so this term is R sigma tilde I1L. Now, sigma tilde is defined as R transpose sigma R. So this is then, because matrix R is orthogonal, this is the same as sigma R I1. And sigma R I1 is by definition sigma IK RK1. However, this is nothing but the definition of NK. So this is the same as sigma N I L. Okay. So this is also Ni, and sigma tilde 1 1 is N sigma N. So we find that this is the same thing as sigma Ni minus Ni N sigma N. So we are happy if this can make us happy. We reproduce this equation. Okay, so this is how you see that evolution of finite time Lyapunov exponent, as long as you don't care about situation where these rows are equal, and there are situations where you do care about that. I will speak about that. So as long as you can assume this inequality, the evolution of lambda 1, which you define in terms of this sigma 1 1 tilde, and in terms of this unit vector of direction between pairs, is simply the same thing. Okay, so this is already quite remarkable because well, it shows to you the connection between things, and you understand that matrix degrees, how matrix degrees of freedom capture this evolution of vectors. And the only thing which we need to do for getting the same thing for lambda 3 is to repeat this calculation a bit differently. So to do it, let's do it the same thing for lambda 3. So we start with, so let me do it. So our result so far, which I want to keep on the board, is that lambda 1 of t equals 1 over t integral from 0 to t sigma 1 1 tilde dt prime. In fact, equals, and equals, it's really equals deterministically in the sense that it's not different at large times from this, which the formula which we had previously, provided that we can assume that rho 1 is much larger than rho 2, much larger than rho 3. All right, so this is about fluctuating value of finite time Lyapunov exponent, because we can use it not only for averages, which is not only for Lyapunov exponent in the limit of infinite time, but we can also use it its finite time version. This is true at finite times, provided these inequalities hold. Okay, so it's deterministic equation. So now we want to keep this, and we consider lambda 3 of t, which is defined in a similar way. It's 0, integral from 0 to t, sigma tilde 3 3 dt prime, and you do the same thing. So in this case, you do not have any insight from this type of vector equation. you simply study the matrix equation, and you find out that it also reduces to vectors. So how do you find it? Again, you use the definition. So sigma tilde 3, 3 is by definition R transpose sigma R 3, 3, which is R transpose 3K sigma KL RL3, which is sigma KL RK3 RL3. And of course, you can do similar thing, in fact, with sigma tilde 2, 2. The difference will come from another direction, so that you really need to use it for 3, 3 or 1, 1, and not the intermediate Lyapunov exponent. So again, you see that if you define vector P K as RK3, then this is a unit vector, so we can designate it with this hat. So P dot P is 1, because R is orthogonal matrix. So orthogonal matrix is composed of rows which are orthogonal vectors. So what remains is to see if this representation, which you get in this way, so you can write it as P sigma P, if you can get anything useful out of this representation, in the sense that if this P obeys a closed equation. So to see if it obeys the closed equation, we proceed as before. So we consider d dt of ith component of this vector. So this is d dt of Ri3. And then we use the equation, which is that this is R omega 2 I3, which is Rik omega 2 K3. And then you go again to these equations, which we had for omega 2. And I'll do it again. So I'm looking at the formula from the paper, which goes after A2. I see that K here must be smaller than 3, because for K equals 3, this is 0, because omega 2 is antisymmetric matrix. So for K smaller than 3, I look at the formula where the former index is, so the first index is smaller than the last index. And I find that omega tilde, or omega 2 K3 is going to be equal to, so IK, so K is larger than I in this case, so I can forget about this term, and I get sigma tilde Ki, where K is 3, so sigma tilde 3I. Okay. So this is straightforward thing where you use these inequalities in order to simplify omega 2, which we derived. I only need to see if I didn't make any mistake here. So K is 3, so this is negligible. This is sigma tilde 3I. And, oh, okay. So the sign is different. So it's with minus. Okay. So this is what I get from looking at the solution for omega 2, which we have. It's straightforward. You will not have any problem doing that. You have simply very different exponential terms in terms of magnitude. You compare them and you get this result. So then we can write that this is equal to minus Rik. And of course, okay, so K, of course. Okay. Yes. All right, so then you have here sigma tilde 3k, and again you sum over k, which are smaller than 3, so you don't include k equals 3. So you see it gets to very similar calculation. So then this, so let me separate this thing. So then you can write it as minus r I k sigma tilde 3k without any limitation on k, and then plus r I3 sigma tilde 3 3. All right, so we look at what we obtained. So we find that, so Rik sigma tilde 3k is nothing but sigma tilde R transpose 3I. Then, so you see that this is sigma tilde 3k R transpose ki, which gives you this. So this is because sigma tilde is R transpose sigma R, then this is the same as R transpose sigma 3I, which is, again by definition, it is R transpose 3k sigma ki, which is sigma ki times, so RK3, which is PK. So PK. All right, so this is our calculation of this term. So our end result is that if we define P unit vector in this way, then this vector obeys this equation that dP dt equals, and here we have minus sigma ki pk. However, this is nothing but minus sigma transpose, which acts on p. Okay, because this is sigma transpose ik. And then you have this term, which again, according to our definition, this is pi times p sigma p. So we get here plus p sigma p. Now, what remains is that we can, of course, rewrite this as, well, let me do it on the board. So I will not simply erase this, I'll do this step. So this is minus sigma transpose, which acts on P, minus P, and here you write P minus sigma transpose P. Okay, and finally, lambda 3 of T. So lambda 3 T equals 1 over T, integral from 0 to T, P sigma P, by definition, which we can write as minus lambda 3 equals 1 over T, integral from 0 to T, P minus sigma transpose P dt prime. Okay. All right, so this is our result. It tells you quite a lot. It's a bit tedious. Again, you see it's straightforward. However, you need to be careful in calculations. So the end result is in fact very rewarding in my view, because what you find is that you can study statistics of this length of the axis of the ellipsoid or finite time Lyapunov exponents by considering two coupled vector equations on unit vectors, and this is significant reduction in the number of degrees of freedom. So usually people do study matrices, and matrices, of course, because it's not matrix W is not symmetric, it has unit determinant, which leaves you with 8 degrees of freedom. So it's not something which, and here you have only 4 degrees of freedom, because these vectors P and M, each of them is unit vector. So each of them has simply defines a direction which is 2 degrees of freedom. So you reduce the number of degrees of freedom which you need to compute by a factor of 2. It's a most significant reduction, which, well, if you recalculate it, it means that instead of, say, half a year of calculations, you can do it in 3 months. So it's, if you think in this way, you understand that it's worth to do this kind of calculations, because in the worst case situation, they will take you 1 day to reproduce it or simply to rewrite it from here, and it's really saving time, computational time. So our conclusion is this, that you can get whole statistics of finite time. Let me write this result kind of in a, I simply want to write it together so that you can have a look and maybe use it in your work. This is a result which, as I told you, is not published. So if you use it, you can be, well, there will be no precedence to this thing. So we have this representation for lambda1. So let me already erase this representation in terms of sigma tilde. So lambda1 of t is this. Lambda3 of t is this. P, so minus lambda3 of t. So this is simply a way to remember this result, is that, so lambda3 is negative. So this is why you want minus here, because this type of system will always produce a kind of positive Lyapunov exponent. So positive average of this quantity, which is why we need the minus here. And the vectors n and p obey these equations. So sigma n minus n and sigma n, and dp dt is sigma p minus p p. Well, okay, I forgot, of course, minus sigma transpose. So it's minus sigma transpose p minus p p minus sigma transpose t. That's it. All right, so this is what you need to study, and the only thing which you might want to remember is that this is the whole set of finite time Lyapunov exponents, because lambda2 is simply minus lambda1 minus lambda3. So this is by incompressibility. So this is the whole set of finite time Lyapunov exponents, and as long as you want to consider statistics for these inequalities, you can use, so the only thing which I might add here, that this is ρ1 over t, and this is minus ρ3 over t, so that you also have on the board the definitions of rows. Okay, so these are the inequalities which we need, and once they're true, so you consider not only the bulk of the events. So most of the statistics is at values of rho I, which are lambda I infinity t. So this is where, say, normalization integral is, where this is where most of the initial conditions bring you within some finite but large but finite time. However, there are deviations. Deviations are relevant for most of the properties which you are interested in. For instance, we will briefly consider the problem of passive scalar, where you want to consider mixing by the flow. And mixing means that you have that, you say, put some dye inside the flow, say red dye, and you watch it and you see that gradually it becomes smeared all over the volume. And you want to know how fast this happens and how soon you will see that the color is uniformly spread over the whole volume. So this is type of the problems, for instance, where you can consider this. And sometimes you want to know for the moments of this concentration of dye, you want to know large deviations from this behavior, because you will see that these large deviations again exponentially increase the averaged quantity, which is our way of understanding why you need large deviations, because you often want to consider properties which are increased exponentially when you consider ray events, and then ray events matter. Okay, so if so I remind you that we wanted to consider, say, moment of magnetic field energy, or in other words, square of the distance between pairs of particles. And for this quite simple property, average of R square, you still needed exponentially rare in time initial conditions for which this R square grows so fast that these rare initial conditions determine the moment. So quite similar logic holds here. You want to know this probability density function of lambda 1, and let's formulate it in terms of lambda 1 and lambda 3. So from this, okay, so lambda 1, lambda 2, lambda 3 at finite time. So you have the distribution. This time it makes sense to formulate it in terms of this distribution of lambda 1 and lambda 3, which you get from these representations. And to remember that lambda 2 is fixed from the incompressibility condition. So you fix these volumes, fractions of initial conditions for which these lengths of the polymer are much different from their typical behavior. And this matters for lots of physical problems. So this fraction of initial conditions for which these ellipsoids have quite different lengths disappears in time exponentially. So in this formulation, you look at the largest axis and you look at the smallest axis. You study their joint statistics. And for their joint statistics, you only need these equations. You don't need to study matrices, which is why I kind of think that it would be good if you take this away from the course and use in your work in case that you study Lagrangian chaos and turbulence, or for that matter, in any other chaotic system for which you have a spectrum of Lyapunov exponents, which is not degenerate, so at large, which guarantees that at large times this holds. So as long as you study the probability density function of this finite time Lyapunov exponents in the region where these inequalities hold, which means both the main events, the typical events, and also large deviations from them, which still do not violate these inequalities, you can use this description. Once, for some reason, you want events where these become comparable, you need, you would need to return to matrices. In reality, you can do simply asymptotic calculations, and this function will do. Okay, so are there any questions? I would be glad to get them here, because this is where I am kind of, I would want that you, if any of you do some work in this direction, maybe think of this. Anybody? Remarks? Okay, so this is hopefully the board which you will remember. So then we continue to study of finally major stretching direction. All right. So maybe it's time to make a break. It wouldn't make much sense to start this thing. So this we will do after the break. We take some 15 minutes break and then continue for the last hour. Thank you, Emmanuel. Well, I do not even smile. I think it's really very good description. So I hope that it will be useful to you. All right, so our last hour today, the 4th hour, I see that some of you survive, which is good. By the way, how tiring all this is for you? If anybody can tell, because, okay, so never mind, I hope. Well, what other thing which I want really to hear you is, okay, this. So if there is some problem with focus, please tell me. All right, so major stretching direction is something which it gives you very good application of this Jacobi matrix, which allows you to see things simply. And in fact, it will tell you, it will have something to do with Imanov's question on special directions in space, which is, which I'll show you. Okay, so in fact, so I told you that there are kind of 2 sets of orthogonal vectors at each point. One set is from these ellipsoids, another set from eigenvectors of rate of strain matrix. So we'll talk more at this point about the set of vectors which define this matrix M. Or this directions of ellipsoid. So I remind you that we have this equation on orientation vector for separating pair of particles, which you saw many times. So what I want is at this point to study the dependence on initial condition. Okay. So what happens when we change the orientation? Okay, the focus is gone, the focus returned, hopefully. Okay, so how do you study this? You realize that in fact you can define n at time t must be given by w of t at n acting on n equals 0, on n0, divided by the modulus of this quantity. Now, how you see it? Well, you see it simply by definition. So, because dr dt is sigma r, well, something wrong with this color, I think. Let's see. Okay. So, okay, this looks better, yes. So this tells you that separation between 2 particles behaves as Wt r at time 0. Then you recall our definition, which is n of t is nothing but r at time t divided by modulus r at time t, which can you see it? Because I see that it's for some reason. Let me check if I can get you another color. Okay, So r at time t, so this gives you wt r at time 0 divided by modulus of wt r at time 0, and then magnitude of r at time 0 disappears, so you find that this is wt and 0 divided by modulus wt and 0. Now this representation for the orientation vector is very useful because you already know the properties of w, and this is the consideration is from a paper which I think I sent you. It is on synchronization between polymers. So what we are doing at this point is significant to understand that all polymers in turbulent flow will locally point in the same direction. Okay, so this is again, every property which we are studying has concrete physical manifestations and applications, and we do not study things which have simply only academic interest. Okay, so please, when calculations get very abstract, remember this and try to ask questions, because then this will have concrete usages.
Itzhak, can you mark,
Yes.
please, where you ask if it was visible? Top right line. Can you mark again this, right?
This?
Yeah, there is like a blur. You know, the marker was not, didn't have enough ink, and there is.
dr dt is sigma r. This is our equation, which gives you, so our solution was r of t equals wt r at 0. I remind you that we derived it.
Okay, I see.
So we got it by simply Taylor expansion, but the other way around is to use, so the equivalent way is to use this equation, which shows you that this is a solution. So this is n of t, and this is derivation of this representation for orientation vector in time t. And what we will do now, we will actually use this singular value decomposition. So we turn it into a calculational tool with which we can do some calculations, and not only can something which is used for proving some theorems. So then this equation tells you that this is r lambda n acting on n0, and because R is orthogonal matrix, in the denominator you have simply the matrix R can be omitted. All right, so let us look closer at these equations, at this equation. So we realize that n is a matrix which at large times becomes a constant matrix. So we can write it in this way as matrix R, which acts on lambda times n infinity and 0 over modulus of lambda and infinity and 0. So what I did here, I changed n, which depends on time, by constant matrix, because as so I remind you, this matrix n gets constant at large times according to the Oscillator's theorem and according to the actual concrete proof which we gave. So then you realize that lambda is a matrix, again we consider large times, which is dominated, it has one eigenvalue which is much larger than the rest. So this is going to be approximately equal to exponential of rho 1. So because this matrix is diagonal, and you so the term which is delta 1 1 will determine this thing. So it's going to be n infinity and 0 1 divided by modulus of the same quantity. So here we use that lambda is diagonal matrix, which approximately at large times you can simply, in this type of calculations, you can consider it as this matrix. Okay, so you can neglect contribution of other values, as long, again, as you consider fluctuations which are not too different from the typical fluctuations where ρ1 is much larger than ρ2, much larger than ρ3. So we are always working under that condition. So then you see that exponential of ρ1 disappears. And we get that this is something which is given by, let me erase maybe here. So n of t is approximately equal to matrix R, which, so let's write it I, Ri, K, and then component 1 of this vector. So you have well, I need to write here as a vector. All right, how I do it? Okay, so here I need to write it in a bit more detail. So let me write it from here. I apologize for a bit of mess which I do here. All right, so we have Rik. So I'll simply write it in a bit detail. So here we have lambda 1, 1. So the index of summation turns to 1. Then you have this exponent ρ1. Then again, because you need 1, 1, then this is n infinity, 1k, and 0k. Okay? And in the denominator, you have exponent ρ1 modulus n 1k and 0k. Okay, so this is this approximation. This is the only thing which I do. You simply need to do it carefully, and this is then what you get. So we are getting there. So the only thing which remains is to observe that this is some constant. So this simply disappears. So this disappears, this disappears, and this becomes Ri1, which is a unit vector because of orthogonality of matrix R. This is similar to what we had before. And we find actually a remarkable result, which is that this term is independent of initial condition. So this is independent of n0. Okay, so all these approximations brought us to very simple understanding of what this matrix R is. Okay, so it tells us that actually all vectors, all pairs in the limit of large times are going to point in the same direction, and this direction is nothing but the direction of largest axis of this ellipsoid. So ellipsoid which turns, say, to a pancake still have one largest axis. So if this is radius epsilon, this is epsilon to power times exponent of ρ1, and this is the direction Ri1. So it's a vector, okay? So equals and I asymptotic. All right, so this explains to you the meaning of this matrix R. Then you can consider that other. So this tells you that the first column of this matrix actually is direction vector of the major axis, and then you can convince yourselves that the rest of the columns give you the directions of the remaining axis of this ellipsoid. And remarkably, typically, there is no dependence on n0. So in the limit of large times, they all point in the same direction. Now, this has very simple meaning, which is because this tells you that effectively any point, any volume behaves as if it is in so-called hyperbolic flow. So hyperbolic flow, let me give you an example in 2 dimensions. It's something which I guess you do know. Who does not know what is hyperbolic flow? Hyperbolic point. Okay. All right, I will make an assumption that you all know this. And then, okay, thank you, Pavel. All right, so simplest example of hyperbolic point or hyperbolic flow is 2-dimensional situation where you have matrix of velocity gradients, which is diagonal matrix of this sort. So you consider how trajectories will evolve. So say this is direction where particles, so dr dt is sigma r. Okay, so this is the simplest example. Then these points, the points on this axis undergo contraction to 0. However, any point which is a bit outside of this axis will eventually go here. And this is, so these are streamlines, okay? What I draw with these arrows. And this is why it's called hyperbolic points, because this, you see that typical streamline, which starts anywhere besides directly on the axis, is a hyperbolic curve. All right. So our understanding of evolution of small volumes of fluid actually tells you that in the limit of large times, every point becomes effectively a hyperbolic point. So it tells you that in fact things are getting extremely simple due to randomness. Okay, because in usual flow, it's not true that any point is hyperbolic point. You have different topology, things get not trivial. In contrast, in turbulence or in any other random flow at large times, everything. So this tells you, this picture tells you that if you consider in this flow a small ball, which in 2D is a circle, then this circle will become an ellipsoid of this type. Okay. So again, this is the same evolution which we considered. So necessarily circle becomes an ellipse, and this ellipse has this form. So in the end, you take any initial orientation. So let's consider this orientation. So you have, this is reference point. This is our R. And in the limit of large times, this point will be here. So the vector n will point in this direction, okay? And this is the same thing for any point R in the limit of large times. All points will be directed along this direction. So again, in the limit of infinite times, this ellipse in fact will become simply a line along this axis, okay? So this is the meaning of these things, that different vectors start to point with time in the same direction. And in 3D, the generalization is direct, that you have in the limit of large times, this line, they effectively, all vectors will be pointed along this largest axis, and you don't really, yes, it is a pancake. Yes, there is another dimension which grows. However, the main direction, which is much larger than the rest of dimensions of the ellipsoid, will actually determine the direction of most of the vectors n. So this is the meaning of this special direction in space. And it is this direction which we call major stretching direction, because simply it determines a major component of stretching. So it's a bit the name reflects what it is quite adequately. The flow stretches things mainly there. So it's major stretching direction. Another thing which it tells you is that you can get, so the geometric meaning of this matrix R. This matrix R is the matrix which specifies the directions of this ellipsoid. In contrast, the matrix N provides you those special directions of initial conditions where the separation proceeds along the rates lambda1 or lambda2 or lambda3. Please, for this, review again our formulation of the oscillators theorem, where we spoke about the meaning of eigenvalues of n. So at this point, you hopefully understand the physical meaning of all terms in this decomposition. So this matrix N defines eigenvectors, special directions at time equals 0. So these are directions which evolve with different rates. So these are called stability directions. So if you encounter the words stability manifold, then this is that. This tells you directions of stretching and contraction. So directions are read from the columns of orthogonal matrix, okay? So orthogonal matrix is, so 3 by 3 orthogonal matrix is a matrix which is composed of three normalized eigenvectors which are orthogonal to each other, okay? So direction of stretching and contractions. And lambda provides you the length of this ellipsoid. So at this point, I hope that you understand that this decomposition really tells you a lot about what happens in the flow locally. The remarkable thing is that it's completely deterministic representation. We don't do any averaging. We simply speak of typical properties of these matrices R, lambda, and n, and we find that they kind of reflect very generic, very robust behavior, where all balls at any point in space evolve into ellipsoids with directions which rotate in space, because matrix R, I remind you, rotates in space, rotates all the time. It changes according to this R omega 2 derivative, where omega 2 is roughly this antisymmetric component of the sigma tilde, where sigma tilde is R transpose sigma R. So you see that the rotation of this matrix actually tells you how this ellipsoid rotates in space. This tells you what are the special initial directions which separate at different rates. And finally, this tells you how the axis evolves. So please make certain that you understand this, because this is the essence of all this, the physics behind all these calculations which we did. It's time to get some application for this, and the application is quite immediate, which is to polymers. Our understanding that all initial directions will point in the same direction means that actually polymers which are stretched in the turbulent flow, if they are stretched, they will be stretched in the same direction. So if you spread some number of polymers inside the flow, they start from some different initial configurations. However, if they are stretched, the stretching will make the end-to-end distances to point in the same direction, which means immediately that polymers are going to interact with the flow in a collective way, where you can define the field of their local orientations, which will specify their direction and their length. Okay, so if they start from the same, roughly the same initial length of the coil, then they will point in the same direction. Or you can, in fact, you don't really care about their length, because you can simply sum them. They all point, their elasticity kind of, their elastic interaction with the flow goes in the same direction. So they collectively kind of give elasticity to the fluid and want to contract in this direction. So there is a special local direction where the fluid wants kind of to contract under the action of stretched polymers. So we will use this field. Before we do so, I want to speak about the field which this major stretching direction defines for us in space. So you see from this that because at large times so it's completely, so to say, kind of deterministic characteristics. So let me show you what I mean by this. So you start at some point X. Yes, please. David? I have something strange here. David wrote that he wants apparently to ask a question. Then there was some noise and David disappeared. Okay. David, can you hear me? I see that you are unmuted. No, I don't hear you. I see that you are unmuted, but I cannot hear. Oh, I don't know if you can hear me. I don't. Okay. So we have, so think of it. So you start at some point X, which is some arbitrary initial moment of time. And then this point evolves into a point which is q of tx at time t. And at this point, if t is large, we have a special direction. Let me make it like this, which is the typical direction of the asymptotic direction of vector n, which components are in fact Ri1. Okay, so we obtained it starting from some point X. However, there's nothing special about any moment of time in the fluid. So we can instead revert this direction, this consideration, and do it a bit differently. So instead of this, we consider fixed point in the fluid, and we ask what will be the direction defined by ellipsoids which come to this point. In other words, we can, starting from this point, let's call it y, we can build Lagrangian trajectory of fluid particles which arrive to this point. So we can build the past history of these trajectories which come here. And then using those the initial points which are in far past, we will be able to determine a unique direction in space, because this direction actually is independent of initial direction. It's independent also of time, because R has finite time variations. So what you get is that there is some special direction in space, which depends on...
Okay, I'm back. Can you hear me now?
Yes, I can.
Okay, perfect. Sorry. So I got a bit confused about the last part that you mentioned, where all the polymers are oriented in the same direction. I don't know if I understand that. Perhaps I'm not understanding the problem that we're trying to solve. I understood yesterday that the polymers were getting oriented or stretched locally by turbulence. So I will expect that to be like the orientation there to be random. Or are we now considering some kind of macroscopic flow where in average the flow is all oriented in one direction? Is that the case, or what am I missing?
Well, this is what we are talking about, that there is, at each point in space, there is a special direction where everything which is stretched will be pointed, okay? So there is some special, so when the flow, so, okay, the statement is like this. So the flow, to start with, stretches things, okay? So if you take a ball, it is stretched into some direction, and other directions can be stretched. Usually they are. There is one direction which is stretched and the other is contracted. However, we speak of major direction of stretching where most of the things develop, okay? So most of the, so if you take a ball, most of it will be stretched into this direction determined by this first Lyapunov, finite time Lyapunov exponent. So this direction does not depend on the initial orientation. So this is what this whole thing is about, that because of these properties of W, that effectively each point in space is a hyperbolic point. So this assumption, in fact, is used in theory of dynamical systems. It's called hyperbolic systems, where you make more or less the same assumption that each point is a hyperbolic point, but for non-random systems, it's not so trivial. It's an assumption. So in turbulence, we are kind of guaranteed that this is going to be true. So then polymers are, so because the flow stretches things in certain directions, so try to think that effectively the flow is this, if you think about three-dimensional case, very roughly, the flow is simply this, okay? Times R, of course. So you are, polymer is found in a linear flow with effective diagonal structure. So here I don't care about geometry and rotations. So every polymer is going to be stretched in the same direction. So whenever, so they may start from different initial lengths, but a bit different, from different initial orientation, but in the end, they're all stretched in the same direction, and this is why they get parallel. And this direction is the major stretching direction.
All right, but is this locally at the length scale of whatever turbulent effect we're trying to study, or this is, or what you're describing is a macroscopic flow?
Both, because locally, so polymers are assumed to be much smaller than the scale of smoothness of the flow. So in this sense, so think of it, you put some coils inside the flow. These coils are in the same linear flow. So we assume that the distance between them is much smaller than the local viscous scale. Then the flow stretches them, but it's very intuitive. It stretches them in the same direction. Okay, so when they are stretched, they're pointed in the same direction. It's not something. So initially, yes, it was random. This, say, was a bit in that direction. This was a bit in that direction. But then the flow comes and it stretches them. They're all kind of, think that you have Dow, okay, and you kind of, you have some initial, say, this was one polymer. You stretch it in this direction, so with time it becomes this. Then you had a bit different. So these are random. The initial balls are random. So that was another ball. It will still be the same thing. Okay. So All right. So lastly, this is about also macroscopic degree of freedom, because this orientation, in fact, as I'm explaining at this point, is a field in space and time. Okay. So this understanding that things which are stretched for some time in the flow will point in the same direction allows us to introduce a field which gives you the local orientation of this this local major stretching direction. So this field can be defined. There is a bit nicer way to do it, to define it, which I will show you later. However, at this point, I want that you understand that this major stretching direction is simply you tell that this is the special direction into which every stretched thing which was for some time inside the flow will point. Okay, and it's unique, identical direction, which signifies what this effective hyperbolic point is in the limit of long evolution time along the trajectory which arrives at the point which we are considering at this moment of time. So this is field in space. Okay, it does not, uniqueness of this major stretching direction, uniqueness of this orientation, its independence of initial condition. This is what allows us to define this field, which means at each point in space, at each moment of time, there is a unique direction at that point, which in fact accumulates information on past stretchings, which you kind of imagine in your mind could occur for things which arrived at that point. Okay. All right. So this, of course, has to do with this R. So R and this N are going to point in the same direction. This also gives you understanding of this relaxation to the same. So I told you that we start with this equation dm dt, which is sigma n minus n sigma n, and initially the things depend on initial condition. Well, initially things depend on initial condition is not a very good sentence, but at early times the evolution of n, of course, depends on what it was originally. However, with time, all of them point in the same direction. So you can tell that n at time t, according to this definition, is equal to this field taken at point which is q of tx. Okay, so this is independent of initial condition, and this is our major stretching direction. So this already allows you to get this first Lyapunov exponent, and of course it refers to this representation of first and third Lyapunov finite time Lyapunov exponents, which we considered before. You have the same fact also for vector p. So this allows you to represent this noise sigma n as, in fact, n at time t q of tx. Let me give you here the explicit form, times grad I vk taken of t y at y, which is q of t and x. Okay, so this is the effective definition which you can use inside these fluctuations of lambda 1 which I wrote, or lambda 1 and lambda 3. You can claim the same thing about vector p, which would define the major contracting direction. So if you consider the same thing for, so I remind that we have this vector p, which is determined by the same type of evolution. However, you use the matrix which is minus sigma transpose instead of sigma. you can apply the same study with another matrix. So let me show this to you. So how you describe this P, okay? It's completely the same description. The only thing which you need to notice is that if you consider that equation that dtw is sigma w, implies that dtw minus 1 transpose is minus sigma transpose w minus 1 transpose. So in other words, when you change sigma to minus sigma transpose, you change w to w minus 1 transpose. That's the only change which you need to do. So let me show how you derive this. So the derivation is kind of simple. So you start with w minus 1, which is 0 by definition of inverse matrix. Then if you use this equation, if you take, okay, let me write it in detail. So this is dt w minus 1 plus w dt w minus 1. Now you use this equation, so you get that this is sigma, and here you have w times dt w minus 1, and from this equation you get that dt w minus 1 is minus w minus 1 times sigma. Take transpose of this equation, you find that dt w minus 1, well, this is not a good part of this board. So from this equation, you get that dt w minus 1 transpose is, you take transpose on both sides, is minus sigma transpose w minus 1 transpose. In other words, you get that solution of this equation for P, which I forgot to change here, is that P at time t, by the same token, is w minus 1 transpose at time t times P at time 0, divided by the modulus of the same thing. Okay, so these are kind of conjugate evolutions, and there is a good reason for that, because in some sense this third or the major contracting direction tells you evolution of wave vectors or time reversed evolution. You can also see this in this way, and you can then consider the say the symmetry of time reversibility. If there is time reversibility, there can be symmetry from sigma to minus sigma, and then you need to see whether transpose operation, whether statistics is also invariant under the transposition, and if yes, then in fact this must have the same statistics, and you can claim that lambda 3 is minus lambda 1. So for time reversible statistics in incompressible flow, in fact you do have this fact that lambda 3 is minus lambda 1. Okay, you can prove it from here. All right, so all these considerations refer to this observation that in the end, what you have is two special vectors at each point, which you can use in this study of major stretching direction, largest and smallest axis of this ellipsoid. And from that, you can get the statistics of all finite time Lyapunov exponents, because the second axis of the ellipsoid is defined by incompressibility condition. So this allows you kind of to get more insight into this, what it means that we were telling all the time that n must relax to some steady state in order. So when we represent lambda 1 as average of n sigma n, I told you that you need that n is already in the steady state. And at this point, you understand in detail what the steady state means. It means that in this formula, you simply need to use the local major stretching direction And then you can, in fact, do this averaging in many ways, which means this. Once you determined the local major stretching direction, you don't need to average over initial positions as we did originally. So we define this averaging by average of over initial conditions. In fact, you can do completely usual space averaging in space at given moment of time. So you can consider this sigma as simply local value of gradient of the flow. You consider the component of local, and of course, this is equal to NSN, where SIK is rate of strain matrix, because we consider diagonal component, which is 0 for the antisymmetric component of the matrix of velocity gradients. So you consider local rate of strain matrix. You consider its component along the local major stretching direction, and then you can simply average it over space. And this again will give you this first Lyapunov exponent. So this gives you other ways of making the measurements in processing the data. All right, we'll talk about it a bit more next time. We finish for today. If you have any questions, I must finish at this point. So please ask them by email. And thank you for today's lecture.